The northern lights, or aurora borealis, are a mesmerizing spectacle that has captivated humanity for millennia. Their ethereal dance of light across the night sky evokes wonder and mystery, inspiring countless myths and legends. But what exactly causes this breathtaking display? Let's find out today on Why Is. The answer lies in the heart of our solar system, with the Sun, our nearest star. The Sun is a massive, fiery ball of plasma constantly undergoing nuclear fusion. This process generates immense heat and light, but it also produces a continuous stream of charged particles, primarily electrons and protons. This energetic outflow is known as the solar wind. The solar wind is not a gentle breeze. It hurtles through space at speeds exceeding 1,000,000 miles per hour, carrying with it the Sun's magnetic field. Earth, like a tiny vessel navigating this cosmic sea, is protected by its own magnetic field. This invisible shield, generated by the movement of molten iron within the Earth's core, deflects the majority of the solar wind away from our planet. However, the Earth's magnetic field is not uniform. It weakens near the poles, creating a funnel-like effect that channels a portion of the solar wind towards the Earth's upper atmosphere. This interaction between the solar wind and the Earth's magnetic field is the catalyst for the auroral display. But how does this invisible energy transform into the vibrant colors that illuminate the night sky? To understand that, we need to delve deeper into the Earth's atmosphere and the complex physics at play. The solar wind is a constant reminder of our dynamic relationship with the Sun. It serves as the fundamental driver of space weather, influencing everything from the intensity of auroras to the potential disruption of our technology. By understanding the solar wind's role in auroral displays, we gain valuable insights into the interconnectedness of our solar system and the forces that shape our planet's environment. The solar wind, as we have seen, provides the raw energy that fuels the aurora borealis. However, this energy is not light in itself. Instead, it's a cascade of charged particles that interacts with the gases in Earth's upper atmosphere, triggering a mesmerizing transformation. When the solar wind reaches Earth, it encounters the thermosphere, the outermost layer of our atmosphere. This rarefied region, extending hundreds of miles above the Earth's surface, is home to primarily oxygen and nitrogen molecules. The energetic particles from the solar wind collide with these molecules, transferring their energy and exciting them to higher energy states. As the excited molecules return to their normal, lower energy states, they release the excess energy in the form of light. This process is akin to how a neon sign glows. The electrical current excites the gas within the tube, causing it to emit light of a specific color. In the case of auroras, different gases produce different colors. Excited oxygen molecules typically emit green or red light, while nitrogen molecules produce blue or purple light. The blending of these colors creates the diverse palette of the auroral display. The altitude at which these collisions occur also influences the color of the aurora. At lower altitudes, where oxygen is more abundant, green auroras dominate. However, at higher altitudes, the rarefied atmosphere allows excited oxygen atoms to emit red light, resulting in the less common red auroras. The intensity and colors of the aurora can vary dramatically depending on the energy and composition of the solar wind, as well as the density and temperature of the Earth's atmosphere. Intense solar activity, such as solar flares or coronal mass ejections, can amplify the solar wind, resulting in brighter and more extensive auroral displays. Understanding the physics behind auroras not only unravels the mystery of their mesmerizing beauty, but also sheds light on the complex interactions between the Sun and Earth. This knowledge is crucial for predicting space weather, which can impact satellite communications, power grids, and even the health of astronauts in space. Furthermore, the study of auroras provides a window into the fundamental processes of energy transfer and light emission in the universe. The captivating displays of the aurora borealis are not evenly distributed across the globe. They are predominantly confined to specific regions surrounding the Earth's magnetic poles, forming a ring-like structure known as the auroral oval. This oval is not a static feature. It expands and contracts, shifts, and morphs in response to the ever-changing conditions of the solar wind and Earth's magnetic field. The auroral oval encircles both the north and south poles, creating the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. These ovals are typically centered around the magnetic poles, but they can expand significantly during periods of heightened solar activity. During geomagnetic storms, when the solar wind is particularly intense, the auroral oval can expand to lower latitudes, bringing the mesmerizing lights to regions not typically associated with auroral displays. The size and shape of the auroral oval are influenced by a variety of factors. The intensity of the solar wind plays a crucial role, as stronger solar winds inject more energy into the Earth's atmosphere, driving the aurora to lower latitudes. The season and time of day also affect the oval's visibility. The auroras are most visible during the winter months when the nights are longer and darker. Additionally, the auroras are more likely to appear during the hours around midnight, as this is when the Earth's magnetic field is most aligned with the solar wind. The auroral oval has been a subject of fascination and study for centuries. Early observers, lacking the scientific understanding we possess today, often interpreted the auroras as supernatural phenomena or messages from the gods. Indigenous cultures around the world have rich oral traditions and folklore surrounding the aurora, reflecting their deep connection to the natural world. Modern scientific tools, such as satellites and ground-based observatories, have allowed us to map the auroral oval in detail and study its dynamic behavior. This knowledge is not only crucial for understanding the fundamental processes that drive auroral displays, but it also has practical applications in predicting space weather and its potential impacts on our technological infrastructure. The charged particles that create the aurora carry electric currents, and these currents can induce electrical surges in power grids, pipelines, and other long conductors. In extreme cases, these surges can overload power systems, leading to blackouts and disruptions to essential services. Radio communications can also be affected by auroras. The ionosphere, a layer of the Earth's atmosphere that reflects radio waves, can be disrupted by the energetic particles that create auroras, leading to interference and outages in communication systems. The impact of auroras extends beyond our terrestrial infrastructure. Astronauts on the International Space Station, orbiting within the Earth's protective magnetic field, are exposed to higher levels of radiation during intense auroral displays. This radiation poses potential health risks, and space agencies carefully monitor solar activity to ensure the safety of astronauts in space. The allure of the Northern Lights has transcended scientific inquiry and has become a cultural phenomenon, drawing people from all corners of the globe to witness its ethereal beauty. The aurora borealis has become a symbol of wonder and inspiration, fostering a sense of connection to the cosmos and our place within it. Aurora tourism has surged in recent years, with travelers venturing to high-latitude destinations like Iceland, Alaska, Canada, Norway, and Sweden in pursuit of the elusive lights. These regions, nestled within the auroral oval, offer prime viewing opportunities, attracting photographers, adventurers, and those simply seeking to witness the magic of the aurora firsthand. The quest to witness the Northern Lights is often a transformative experience. Standing beneath a sky ablaze with vibrant colors, many feel a sense of awe and humility in the face of nature's grandeur. The aurora's fleeting nature adds to its allure, as each display is unique and ephemeral, a momentary masterpiece painted across the celestial canvas. For photographers, capturing the aurora's ephemeral beauty is a challenging yet rewarding endeavor. The long exposure times required to capture the faint light necessitate patience and skill. Time-lapse photography has emerged as a popular technique, compressing hours of auroral movement into a few mesmerizing seconds. The Northern Lights have also become a source of inspiration for artists, musicians, and writers. Their ethereal beauty has been captured in paintings, sculptures, and musical compositions, reflecting the profound impact they have on human creativity. See you next time on Why Is. Share the video with someone, like and subscribe to our channel if you learned something today. And don't forget to press the bell so you don't miss any new videos. And let us know which why you want to find out next. Until next time. Why are you still here? I said I'll see you in the next one.